Another interesting sort of work situation that we can analyze using integrals is filling tanks. So suppose that we have a water tank that's a cylinder 10 meters high with a circular base that has radius 3 meters. So something like this. So at the base we have 3 meters and it's 10 meters high. How much work does it take to fill the tank from an inlet at the bottom? Fill it with water, I guess. So there's some sort of input here that we can pump water into, and as we pump in water, the level of the water is going to increase until finally it gets to the top of the tank. Well, you can see to fill this tank, we're going to have to take water that's starting at the bottom of the tank and move water up to the various heights to fill the tank, since the tank is above the place where we're filling it from. So every slice of water, right, every horizontal cross-section of water in this tank is going to be moving a different distance. So what we can do is figure out the work for the slice of water at height x. So we'll find the force that it takes to lift it times the distance that we have to lift it, and then we'll integrate to add up all of these bits of work to get the total work. So let's look just at the slice of water that's at height x. So we need to know the force we have to exert to lift this slice of water, but we have to counteract gravity. So the force is 9.8 times the mass of this slice. So that's the force. And then the distance that we have to lift this slice, well, it starts at height 0 and it goes up to height x. So the distance we have to lift it is x. Okay, so 9.8 times, what is the mass of this slice? Well, we know the density of water is 1,000 kilograms per cubic meter. So if we know the volume of this slice, we could multiply by the density. So density times volume of the slice times x. So 9.8 times the density is 1,000. And I won't keep track of units, but they are all compatible, right? We're measuring masses in kilograms, volumes in meters cubed, and distances in meters. So everything is compatible here. So now we need to know the volume of this slice. Well, if you look at this slice, it's an infinitely thin cylinder, essentially. So the height of that cylinder is, well, it's infinitely thin. So the height of the cylinder is dx. And the area of the base of this cylinder, well, the base of this cylinder is a circle with radius 3 meters. So the area of the base is the area of that circle. So it's pi times 3 squared is 9. And then don't forget the x on the end here. All right, so putting this all together, we have 9.8 times 1,000, so 9,800 times 9 times pi times x times dx. So this is the work that it takes to lift the slice at height x. So the total work, we need to add together all of the bits of work for each slice, but we need to add together all of the slices. And since the tank goes from height 0 to height 10 meters, the integral is going to go from 0 to 10. Okay, so now we can integrate. All these constants in the front we can move outside. So 9,800 times 9 times pi times, and then do an integral. So 1/2 x squared from 0 to 10. So 9,800 times 9 times pi. 10 squared is 100 times 1/2 is 50. And then plug in 0 for the bottom bound and you get 0. So we can dump this all into a calculator to figure out how much work it takes. So 9800 times 9 times pi times 50 is 1.385 times 10 to the 367 joules. So a fair number of joules. A joule isn't a ridiculously huge quantity of energy, so 10 to the 7th isn't a ridiculously huge quantity of energy, but still, it's a fair amount. Okay, let's look at, so something that made this situation a little bit easy to analyze is that every slice of water has the same shape. But, you know, that happened just because our tank was a cylinder. So what if our tank has a slightly more interesting shape? For an example, let's have a water tank that is a pyramid that's 5 meters tall and 2 meters along one side of its base. And we're going to fill this from its lowest point. And let's look at two situations. So let's look at the situation where, let's figure out how much work it takes to fill with water if the tank is point up. And let's look at how much work it takes to fill if the tank is point down, so that the square is up. So for this first one, we're going to have our tank like this. Okay. Now each cross section here is a square, but as we go from the bottom to the top, the squares change size. So that's going to make our calculation a little more complicated. If we just look at a side view for this tank, looks like this, and it's 5 meters this way, and 2 meters this way, right? So we can actually use similar triangles because here's a similar triangle right here, and so the ratio of this height, let's call that y, and this width, let's call that x, is the same as the ratio of 5 to 2. So y over x is equal to 5 over 2, and we probably should write things in terms of how far we are from the top of the pyramid. So let's use y for our independent variable. So we need to solve things for x. So this means x is 2/5 y. Okay, the area of one of these slices here, the area at height y, or sorry, we're measuring y down from the top here. So the area y units down from the top is just the square of x, because the slice here is a square. So that's, right, here's x, 2/5 y. So when we square that, we get 4/25 y squared. So the volume of the slice at height y is the area, so 4/25 y squared, times the thickness of this slice, but it's infinitely thin in the y direction, so that's dy. So the mass at height y is the density times the volume. Density of water is 1,000 kilograms per cubic meter times 4/25 y squared dy. And we can simplify that. So that's 1,000 over 25 is 40 times 4 y squared dy. So 160 y squared dy. So that's the mass at y units down from the top. So the weight y units down from the top is 9.8 times the mass. So 9.8 times 160 y squared dy. And the distance that this slice has to move, here we have to be a little bit careful because, right, we're measuring things down from the top. the distance that the slice at this position has to move is up from the bottom, because remember, we're pumping in water from the lowest point of the tank here. So the distance that this slice has to move is actually 5 minus y. Okay. So the total work here is we're going to integrate from 0 to 5 because we have slices going from y equals 0 to y equals 5. The force we have to exert is right here. So 9.8 times 160 y squared dy, and I'm going to put the dy all the way at the end because that's where I like to have it. And then the distance that this slice is moving is 5 minus y, so put that in here. 5 minus y. Okay, now we have an integral problem, so move the constants out to the front. 9.8 times 160, integral from 0 to 5. We're going to have to distribute this y squared, so 5y squared minus y cubed dy. And then integrate 9.8 times 160, 5/3 y cubed minus 1/4 y to the 4th from 0 to 5. So 9.8 times 160 times 5/3 times 5 cubed minus 1/4 times 5 to the 4th. And then when we plug 0 into this, we get 0. So now it's calculator time, or I guess arithmetic time if you want to work all that out by hand, but I don't at the moment. So 5/3 times 5 to the 3rd minus 1/4 times 5 to the 4th. I made a typo. 5/3 times 5 to the 3rd minus 1/4 times 5 to the 4th. There we go. All right, so number times 160 times 9.8. That's 8.167 times 10 to the 4th joules. Okay, that was with the tip up, I believe. Here, yes. So now let's do it with the tip down. So now we're going to be like this. Okay. Right, so here's one slice, the slice at height y. This time our similar triangle situation still works out the same. So right here's 2 units across the bottom, 5 units tall. For this slice at position y, it's at height y, and its width we can call x. So still we have x over y equals 2 over 5, and so x is 2/5. Okay, so the the weight of this slice is still going to turn out to be the same, so it's 9.8 times the mass, but the mass of the slice of water at this height is the density, which is 1,000, times the volume of this slice. The volume is the square, oh, I'm missing a 9 here, the square 4 over 25 y squared times the thickness, which is dy. So this is the same as before. 9.8 times 160 y squared dy. But when we put this into our work integral, so again, we're going to integrate from 0 to 5, 9.8 times 160 y squared times dy, and I'm going to put the dy over here. The distance that this slice at height y has to travel, now it's not 5 minus y. Now it's just y. So that's different than the last one. Okay. So move our constants outside, 9.8 times 160, integral from 0 to 5 y cubed dy, 9.8 times 160 times 1 over 4, so we can simplify these. This is going to be 40, okay, times y to the 4th from 0 to 5. When we plug in 0, we're going to get 0, so let's just plug in the 5. 9.8 times 40 times 5 to the 4th. Okay, looks like calculator time. 5 to the 4th times 40 times 9.8. 2, 4, 5, 0, 0. So 2.45 times 10 to the 3, 4, 5 joules. All right. So comparing these two, you might have expected that since you're filling the tank with the same amount of water, these two amounts of work would come out to be the same. But like this, with the tank with the tip down, it's on the order of hundreds of thousands of joules, and with the tip up, it's only tens of thousands of joules. So it's actually much easier to fill the tank if the wide part is at the bottom, and that's maybe a bit of a surprise. It makes intuitive sense if you think that if you have the base down instead of up, more of the water is at the bottom, so you don't have to lift it as far. So of course it takes less work. So it seems obvious when you think about it that way.